Good day, students. Welcome to the second lecture recording on Module 6, Reaction Energetics and Food Enzymes. In this section, we're going to focus on the effect that energy has on enzyme kinetics. Okay, just to recap a little bit, in the last recording, we spoke about enzymes catalyzing a reaction whereby the enzyme and the substrate come together, form an enzyme-substrate complex, and then the product is produced. In that whole process, there is work done and there is change that happens whereby the substrate becomes the product. So it means that there's energy involved in there. So what is energy? Energy is the capacity to do work, the capacity or the ability to bring about change. So in relation to enzymes is the ability for the enzyme to break down sucrose into glucose and fructose, bringing those two products as the change. So if we can say that enzymes drive all chemical reactions, so we are actually saying that during all those chemical reactions, there's energy that's taking place. So the energy, as we already know, is all around us. It drives all the chemical reactions, and then it also determines which reaction is going to occur and what products are going to be formed and in which direction will that chemical reaction takes place. Making an example, energy in a closed system, will usually change to either a change in height because of the volume or the change in heat because there'll be change in temperature between the system and its surrounding. So making an example, it's like, let's say during an acid-base titration, let's say HCl and sodium hydroxide, that's taking place in an Erlenmeyer flask that is immersed in ice-cold water, or let's say ice water. So what would happen is, usually because that chemical reaction is taking place, what happens is that the energy that is formed in there will leave the system in the form of heat, and then we are only going to observe that change by seeing the ice starting to melt. So in that way, you already see that the chemical energy that was produced there was then transformed into heat. So that's the relationship between your heat and your chemical reaction. And in the above mentioned example, what happens is that because the heat was released, therefore it means that that reaction was an exothermic reaction, which is very important in terms of enzyme catalyzed reactions. And then alternatively, when energy is absorbed, we all know that that becomes an endothermic reaction. So in terms of enzyme catalyzed reaction or any other reaction taking place, we have to take in consideration the effect of thermodynamics. As we already know that thermodynamics is a study, especially in physical sciences, that actually deals with heat and its relationship with all the other different forms of energy. So what happens is that in this study is whereby the heat is transformed from heat energy and then to work, or vice versa. So that will be thermodynamics. And in thermodynamics, we deal with different systems. We first deal with an open system whereby in an open system, there can be an exchange of matter and energy with its surrounding. I usually make an example of a kettle that is boiling. When a kettle is boiling, what happens is that because if it's boiling, the steam leaves the kettle and it can actually be transferred to the outside of the kettle. So in that way, it exchanges matter and energy with its surroundings. And when you get into a kitchen where there's a pot of boiling water, you can already feel the energy in there. It's much warm. And then second system that we deal with, we also deal with a closed system. The closed system cannot exchange matter with its surrounding, but it can exchange energy. And I'll always make an example of a geyser. A geyser, when it's enclosed in there, what happens is that you can just feel the warmth on the geyser itself, but it's not letting the steam out when it's enclosed, totally enclosed. And then lastly, we talk about an isolated, or what we call adiabatic system, which cannot exchange matter nor energy with its surrounding. And usually make an example of an insulated flask. If you put your hand around the flask, you won't even feel that the water is actually boiling hot. So those are the different systems that we deal with in thermodynamics. But also at the same time, with thermodynamics, we cannot go away from the laws of thermodynamics, especially the one that are mostly related with the chemical reactions where enzymes are concerned. So the first law of thermodynamics, as we already know, is that energy cannot be created or destroyed, but it can be converted from one form to another. An example of this is a warm body that's sitting on a cold block. Then what happens is that after some time, there's exchange of heat energy, and then the cold block becomes warm. So that's the first law. But the second law of thermodynamics talks about the entropy, that all system tends towards a greater entropy of randomness. So what happens is that in terms of our enzymes, we already mentioned that enzymes are proteins, and we already mentioned that proteins at their higher level of structure, they are at the highest entropy because that's its native conformation where it works the most. Okay, so same applies to this. Matter and energy tends to be disordered. Okay, so what happens is that in terms of the second law of thermodynamics, like we already mentioned, we mentioned the random coiling of the tertiary structure of a protein. So the tertiary structure changes to the highest state of entropy as the primary structure changes, and that's due to change in the external factors, and that's the level where the protein function at its best, and that's due to the second law of thermodynamics. Okay, so when we talk about energy changes during a reaction, so in each and every reaction there is some form of energy involved. Okay, so there's different types of reaction. We already mentioned that there's anabolism and catabolism. Okay, so anabolism is when two molecules are joined together to form a product, and then depending on the forces that are driving those reactions, it can either be a forward reversion or a reaction, or it can be forward and reverse reaction. And then you also have catabolism, whereby a product has to be broken down into simpler molecules. And then lastly, you also have an exchange reaction. So those are the different types of reaction that can take place. So in all these chemical reactions where there's a product being formed, whether it was forward, reverse, or forward or reverse reaction, what happens is that the first law of thermodynamics is actually obeyed, because the energy in the substrate is converted from one form to another, whereby chemical bonds are being broken down or are being made up, and then in some form or another there's a substrate that changes into a product. So either heat can be exchanged, or heat can be absorbed, or can be released. Okay, so how do we go about measuring this? You can measure, because the energy changes to work, either the change in height or weight, because now if you change your sucrose to your glucose and fructose, you've already changed. You have gained a product and lost a substrate. Or what happens is that in the very same process, the heat can be produced and increase in temperatures. Okay, so what happens is, when that whole reaction is taking place, what we can do is we can measure the change in free energy. So what is this free energy? Free energy is the amount of energy that's released or gained during a reaction. So by measuring the free energy, we can then be able to conclude as to whether that reaction was spontaneous or not. However, like any other experimental work that is done, it has to be done at constant environmental conditions, like your temperature and your pressure. So based on this, we get to what we call the free energy, or the Gibbs free energy, whereby we calculate it by saying the formula is delta G is equals to the energy of the product minus the energy of the reactant. And in that way, we'll be able to get the free energy. So the differences between the energies of the reactant and that of the final product is known as the energy change, or the Gibbs free energy. Okay, so in that point, that's when we also get to find out the amount of energy that is then required to bring reactants to what we call the transition state. Remember, we said the transition state is a state whereby the chemical bonds are about to break or to meet together for the product to be formed. I made an example of the transition state being, let's say you are pushing a hill or a rock up the hill or a cut, but when you're on the other side of the hill, that rock, you need energy to bring it up to the transition state. When it gets to the transition state, then it will automatically spontaneously roll down due to gravity. So that is the energies that we require. So the amount of energy that's required to bring those reactants into to the transition state, and that energy is known as transition energy. Transition energy is very important in terms of the chemical reaction, because if there's no activation energy to get the reactants to transition energy, then the chemical reaction will not take place at all. Okay, so we spoke about those energy changes. So if delta G is actually negative, it means that the energy was released, products are much simpler, and there's greater entropy. And then it will tell you that that reaction was actually an exothermic reaction, or what we call a spontaneous reaction. However, when you have a positive delta G, then you know there was energy input there, and then the products are more complex. The energy was needed to go against the second law of thermodynamics, and then those kind of reaction are actually endothermic. Okay. So just an exercise. Remember, we mentioned that the free energy is the difference between the energies of the product minus the energy of the substrate. Okay, so just an exercise. An exercise says maltose sugar was produced as a byproduct of partial starch hydrolysis. You guys know what starch is, and you know what hydrolysis is. And this was done by treating with an acid solution at 95 degrees Celsius for 1 hour. The reactants had an inherent energy of 52 kilojoules per mole, and the products 45 kilojoules per mole. So you are given all the product parameters. You are told it's maltose sugar. It was formed during starch hydrolysis, you know. And then the questions are, or the problem to be solved is, the company would like to speed up the process by using enzymes, because 95 degrees Celsius for an hour, it's too long, and the energy that they're using is quite high. So then the first question is just calculate the Gibbs free energy and stipulate the kind of chemical reaction that took place. So it means that you must use the Gibbs free energy to calculate this and then tell us the type of chemical reaction. Easy peasy, isn't it? And then it says name the enzyme that will be ideal for replacing HCl. So which enzyme do you think is then ideal to break down the starch? So that will be your exercise that you have to do on your own. Okay, so back there we started talking about thermodynamics and how it obviously affects the reaction rate. And then we came up with the phenomenon of getting your reactants to the transition state. And then we mentioned that for us to get to the transition state, we need what we call activation energy. Okay, so before going deep in there, we first need to remind ourselves that when we talk about a chemical reaction, we are either talking about a chemical reaction whereby bonds are being broken down or bonds are being formed. Okay, so meaning that some bonds definitely have to be broken down at the start of the reaction, and this will have to require energy. Even if the bonds have to be put together, that will also require some energy. Okay, so no matter how exogenic the overall reaction is, some form of energy has to be added to break the bonds or to get the reaction going. Okay, and this is then known as activation energy. We spoke about activation energy back there, but we didn't explain it like we did now. So some form of energy to kickstart the reaction, that will be the activation energy. So like I mentioned, the activation energy is that energy that the person is going to be using to push the rock up the hill so that it gets to a point where the rock can actually roll itself. Okay? So what happens is that organic molecules definitely contain energy that could be released by the breakdown of a molecule. It does not happen spontaneously. Activation energy must always be provided. Please remember that. So activation energy, normal activation energy in any type of chemical reaction, how is it accomplished? Usually, activation energy is in the form of heat. Why? Because remember, we mentioned that you actually have two molecules that maybe have to be joined, or you have one big polymer that has to be broken down. So with heat, if you bring about heat, the heat increases the motion of molecules. So if it increases the motion of molecules, let's say it's 2 amino acids. So when you are heating those 2 amino acids in a test tube, so by heating them, those different amino acids will start moving around. And when moving around, they are able to move around and align themselves in such a way that the carboxyl group will then be aligned with the amino group, not the carboxyl with the hydrogen. So each and every time when that vibration or motion of molecules is taking place, it has to happen so that those molecules can collide in the right direction. Okay, so it means that you need energy, heat energy, to make those molecules collide. But if we have those 2 amino acids in a test tube and we really want them to form a dipeptide, with an enzyme, we don't need heat at all. The enzyme just brings those 2 together in the right position, and bam, there the peptide bond is formed. So enzymes are then used instead of heat, so we don't need that high of an activation energy. So like I already mentioned, the enzyme will then bring those reactants together and hold them in the correct position with respect to each other. So that's the amino 1, amino 2. It's going to align them in such a way that even if it has to rotate it or flip it or do whatever, but the carboxyl group and the amino group will be in relation to each other so that those 2 can form that peptide bond. Okay? So I'm just making an example. I found this illustration on the internet. I thought this is the coolest thing ever. Okay? So it's showing us that this is the substrate, okay? It's a baby that's wearing a sweater. And then the mother probably is the enzyme, because mothers drive everything, don't they? So now you can see that there's the substrate, there's the enzyme substrate complex. So the product must be a baby that's free of the sweater or the jersey, whatever you want to call it. But when the enzyme comes, it takes the what? The substrate to the transition state. Transition state is a state whereby that jersey is almost out. Okay, do you see that? So I found it very nice to explain the effect of activation energy, and I hope you also find it easy to understand. Okay, so let's go on. Okay, so like we already mentioned that in terms of activation energy, the enzymes always operate in a principle. You know, the tertiary and quaternary structure obviously renders it appropriate to bind with its substrate because obviously of the way it's natively conformed. And then we already mentioned that the enzyme binds the substrate in a key and lock theory. And then what happens is that the enzyme then changes the shape. It distorts the shape of the substrate when it enters. And that's called the induced fit. So by just forming that induced fit, that change in shape of the substrate by the enzyme, that is how it's bringing it to its lower activation energy. So that's all the energy it requires. Okay, so the change in shape then lowers the activation energy by stressing the bonds, and it's like and then gets it to a point where it's likely to break down. So in an uncatalyzed reaction, there you need heat. Then you need to heat up the molecules to start moving around so that they break or they make up. But in an enzyme, it's just the enzyme substrate, and then the enzyme distorts the substrate. That's the activation energy, and it's a lowered activation energy because we don't need or require large amounts of heat. Okay, so here is a diagram showing you the activation energies between an uncatalyzed reaction and a catalyzed one. Okay, so look at the free energy, which is the Gibbs free energy. Okay, and then look at the reactants. The reactants are similar, and then the products are also similar. Okay, and there's no difference in the free energy between the catalyzed and uncatalyzed reaction. But how does this go about? Okay, so if we have sucrose here as the reactant, okay, then what happens is, depending on whether we are breaking sucrose because we are using an acid solution or we're using an enzyme, with that acid solution, we still need to heat up that acid solution to get it to the transition state, to a point whereby the bond is about to break. However, the fact that we have to heat it, it means we are bringing about energy, the activation energy that takes it from the ground state to the transition state is quite high, because we are using heat or energy in the form of heat. Do you see how high that is? However, when you have the enzyme sucrase that is breaking down the sucrose, it just needs the sucrose to just come in contact with the sucrase, distorts and stress the bonds, and then at the end of the day, here in the product, you form your fructose and glucose for both reactions. In both reactions, you are going to form the very same amount of product. It's just that the energy that was required to start the process was quite high for the uncatalyzed one as opposed to the catalyzed one. Okay, so then the activation energy, we already spoke about that. So the enzymes lower the activation energy that's required for the reaction to take place, because you don't need to heat. Okay, so a lower activation energy actually means that there are more reactants that are activated. Because remember, if you need a high energy, let's say you were doing this on a stove where you have your sucrose and you added your acidic water. You have to switch on the stove has to heat up, and then you must put the pot, it must start heating up and all that. However, in a lower activation energy where it's just an enzyme, it means that by the time the pot starts boiling for 10 minutes, with the enzyme, you would have catalyzed a lot of reactions. More reactants would have been activated and taken to the transition state compared to where the heat energy is required. Okay, so the reaction occurs much faster than normal. Like we already mentioned, in an uncatalyzed reaction, the activation energy is achieved by heating the mixture. But in an uncatalyzed one, the activation energy is lower and there's no heat required for that. So that is why enzymes are preferred everywhere, because of time consuming and less time consuming and less energy consuming. So an example of an activation energy, this is just an example, a table showing you an easy biochemical reaction in which hydrogen peroxide is converted to water and oxygen. Usually hydrogen peroxide is used in the dairy industry, especially to sterilize the Tetra Pak. The Tetra Pak is that carton that they use for the UHT milk. So they usually use hydrogen peroxide to actually flush and sterilize those bottles. So what usually happens is that after hydrogen peroxide has sterilized, there is some form of hydrogen peroxide left in there, and we don't want it in the milk. So they usually use the enzyme catalase to break it down. Okay, so this reaction here, whereby hydrogen peroxide is broken down, the hydrogen peroxide is broken down into water and oxygen. So what happens is that we can actually lower the activation energy by using different catalysts. So the first reaction condition, when there's no catalyst at all, is just hydrogen peroxide being left there to break itself into water and oxygen. The activation energy required for that is 75.2 kilojoules per mole. However, if platinum is used, we know platinum is a catalyst. If this reaction is taking place on a platinum surface, the activation energy is lowered. It's actually 48.9 kilojoules. However, if we decide, okay, we actually want to use the enzyme catalase to do the breaking down, it takes energy of 23. So you can already see with an enzyme catalyzed reaction, the activation energy is lower compared to the platinum one, and then when there's no catalyst involved at all. Okay, so then when we talk about activation energy, as we mentioned, it takes us to the transition state where the reaction is about to happen, a product's about to form. But that then brings us to the enzyme kinetics. So what is this enzyme kinetics? Enzyme kinetics deals with measuring how fast or how slow the reaction is taking place. And then it measures the rate of chemical reaction. And this rate of any rate of chemical reaction has to do with speed, is expressed as a change in concentration of a reactant or product in a given time interval. What that simply means is when we have an enzyme or when a chemical reaction is taking place, we want something to form from something. Like we already just mentioned the example whereby hydrogen peroxide is broken down into water and oxygen. So the rate of chemical reaction there is expressed as the change in concentration of hydrogen peroxide or the change in concentration of water and oxygen in a given time interval. So after 5 minutes, what happened? The hydrogen peroxide was broken down into water and oxygen. So as we already know, in terms of whatever chemical reaction is taking place, A plus B is equals to product. That's when we're talking about anabolism. Two substrates can come together, like glucose and fructose can come together and form your sucrose. Or alternatively, the sucrose, which can break down into glucose and fructose depending on the type of reaction. So what we do is we measure the rate of disappearance of the reactants, or we measure the rate of appearance of a product, because either way the substrate is going to be consumed. Remember we said the substrate gets consumed and then we form a product. Okay? Or the two substrates come together to form a product. So either way there must be a reactant and that reactant must be consumed and the product is formed. But remember we said if an enzyme is being used in that reaction, the enzyme never gets to be used up. Okay, so I'll repeat that. So the rate of disappearance of reactants or the rate of appearance of a formation. So if we want to talk about the rate of a chemical reaction, we'll talk about, that's A plus B. So A is equals to minus delta change in A over delta T. B is minus delta B divided by change in T. And P is equals to delta P divided by change in time. So what happens is that we're talking about the concentration. So if we said we're talking about appearance and disappearance, first of all, when something disappears, it becomes negative, it's gone. When something appears, it becomes positive, it comes alive, put it that way. Okay, not the best example ever. But so A is characterized by change in its concentration because A is the substrate and it's going to be consumed. Over some time, there won't be any A left. So A is gone, is negative, it has disappeared. Same applies to B. B is also disappearing over time to form what? The positive product. Let's make an example of this reaction here, chemical reaction. We have sucrose as the substrate. We have sucrase as the enzyme. Then they form the enzyme substrate complex, taking it to the transition state. And then from there, the glucose and the fructose is actually formed. So if we were to talk about the rate of chemical reaction for this reaction here, we would actually say the sucrose is equals to minus the concentration of sucrose over a period of time. Let's say this took 5 minutes. So I'll start again. So the rate of disappearance or appearance, the rate of chemical reaction for this reaction taking place is going to be, is equals to minus sucrose, change in sucrose concentration, over 5 minutes, or change in time. And then for the product, we're going to say plus change in concentration of glucose over change in time. And then for the fructose, we're going to say plus the change in concentration of fructose over delta time, which is 5 minutes. I hope you guys understood that. Easy peasy. And then also in enzyme kinetics, we also talk about the rate of equation for the conversion of a substrate to a product. So there we have it. The velocity will be the change in product over the change in time. So velocity is velocity, that's the amount of product formed in a certain time unit. And then the velocity, obviously the speed, is influenced by factors such as the concentration of the enzyme, the substrate concentration, the temperature, and the pH. So any other chemical reaction that usually takes place, it depends obviously on the factors. Okay, so in the next recording we'll be talking about the different factors that affect enzyme activity.